Hey, this is a quick overview of angular speed or angular velocity. So first of all, angular speed is just how quickly we move through angle, just as regular speed is our displacement over time. Angular speed is angle over time, how quickly we go through angle. And we use angular speed or angular velocity and angular frequency interchangeably. The variable for angular speed is this lowercase Greek letter omega. It's a lowercase omega. It looks like a W. It's not a W. It's a little curlier than a W. It's omega. And since angular speed is angular displacement over time, it has units of radians per second, or units of angle over time. Angular speed is never measured with degrees per second. It's always radians per second. Anytime you see omega, it's radians per second, which is why we always have to work with radians when we're dealing with angular motion. And it's pretty straightforward to calculate change in angle over time. So if we're riding a 120-meter diameter Ferris wheel through 11 full cycles in 5 minutes, what is our average angular speed? Well, our angular speed omega is just our angle that we go through in radians over time. The angle that we go through, well, we went through 11 full cycles, and a cycle is 2 pi radians, so it's just going to be 11 times 2 pi radians. And the time was 5 minutes, so to convert to seconds, we just multiply by 60. 5 times 60 seconds. Multiply those together, we get 11 times 2 pi divided by 5 times 60. 0.23 radians per second. Why is angular velocity useful? Well, let's look at this kind of diagram here. We can see we have two dots going around these two concentric circles, the pink one and the blue one. And they both take the same amount of time to go around that circle. So that means they've passed through the same amount of angle. So these two rotating dots would have the same angular frequency or angular speed. But the blue one has traveled a much, much greater distance in the same amount of time because the circle's bigger. So blue has gone a much greater distance or tangential speed, even though it's going the same angular speed. So we can use angular speed as a way to kind of go between linear speed and angular speed. Sometimes we care more about the angular speed, sometimes we care more about the linear speed. But here's how we can convert between a tangential speed and an angular speed. It's this formula here, and it's given in your data booklet without the tangential. But keep in mind, this is just your tangential velocity. That is your velocity tangent to the circle. V equals omega times r. And really, anytime we're going from an angular variable to a linear variable, we multiply by r. And we can get this just from the arc length equation. If we know that our arc length delta s is equal to r times delta theta, and we know that omega is equal to delta theta over delta t, we just divide both sides by delta t. And the left side becomes speed. The right side becomes r times omega. V equals r omega or omega r. So it really just does come from that. Okay, so let's find some average speeds. A car makes a left turn at a T intersection with a turning radius of 8.0 meters in 1.5 seconds. Find its average speed. Well, what's the angular velocity going to be? It's going to be delta theta over delta t, which is, well, it's a T intersection. That's a 90-degree turn, quarter of a cycle, so that's going to be pi by 2. And the time is 1.5 seconds. So pi by 2, pi over 2, divided by 1.5 is equal to 1.05 radians per second. And if we want the speed, we just multiply by the turning radius. So that's going to be V equals omega r. 1.05 times a radius of 8 meters is equal to 1.05 times 8 gives me 8.34 meters per second. So that's our average linear speed. Okay, part 2, what angular speed is required to go at the same tangential speed around a 12-meter turn? So same tangential speed, which means same linear speed. So we know v, and we know r. V equals omega r, and we're looking for omega this time. So omega is just going to be equal to v over r. Our speed is the same as before, 8.34 meters per second, and r is 12 meters. So 8.34 over 12 gives me 0.698. And meters per second over meters gives me nothing per second, but we just need to know that that's radians. It's a unitless or dimensionless unit. Yeah, so at the same speed, a bigger r gave us a smaller angular velocity. And that's all. Angular speed, angular velocity. Bye.